Hello guys, welcome again to this video. In this video we will be talking about moment generating function for exponential distribution. So in the last video I have explained to you how the moment generating function works and how we derived its properties. So I'll just write down everything that we did in the last lecture because it will be useful in this lecture as well. So this was the basic definition for the moment generating function of any random variable x, and e of expectation of e to the power tx is basically how we define it. There are other definition of course which I am going to write. So these are the representations of the moment generating function. So we have proved all of this in the last video. Now we also did that to recover the moments back from the moment generating function, we need to differentiate the moment generating function n times to get the nth moment. The formula was something like this. Right? So we see that these were the properties that were introduced to us. Now we shall move on to find out the MGF for the exponential distribution. So the MGF for exponential distribution, for that we would need the PDF. So we can write the statement as let x follows exponential distribution with parameter lambda, and its PDF is f of x would be equals to lambda into e to the power minus lambda x greater than 0, right? Therefore the MGF would be this, right? Now we can evaluate it in both ways, but I would try to do it with the integral definition first, and then we will try and evaluate with the the infinite series definition. Okay, so first of all we see that the region of integration is basically 0 to infinity, right? And thus mxt would be equal to e to the power tx lambda e to the power minus lambda x dx. So this is the region of integration 0 to infinity, and this is the function how it looks like. So simplifying, we get lambda comes out outside as it is a constant, and we have 0 to infinity. The powers add up, and we can take minus x common, and we can write it as lambda minus t dx. Now as we know that the integration for e to the power minus ax is just 1 by a, we can see this is basically lambda by lambda minus t, right? This can be written as 1 by 1 minus t by lambda, and when t is less than lambda, we can expand this series as follows: 1 plus t by lambda plus t square by lambda squared, and all the way up to infinity. This would give you n equals to 0 to infinity t to the power n by lambda to the power n, right? So as you can see, the moment generating function is basically this one, lambda by lambda minus t. But what I've done is I've also expressed it for you as a infinite series. How we did that was we divided by lambda and we got this expression. And if you remember from the geometric series, that is equals to 1 plus x square and all the way up to infinity, which is basically n equals to 0 to infinity x to the power n only when mod x is less than 1, right? So this is basically the condition for the geometric series to work. So for here we must have minus lambda less than t less than lambda. That is how it works. So when t is between minus lambda to lambda, this MGF will be possible in form of an infinite series as well. Otherwise it always has the form lambda by lambda minus t. You can always use it to find the moment generating function. So this is the moment generating function for exponential distribution, right? And this type of things although come very rarely, because we do not really need to extract all the information from it, but there is an associated function with it which is called the characteristic function. And the characteristic function is something like this. So for a given random variable x following a PDF f of x, we have so the characteristic function is usually defined by phi x of t, and the definition is so it is basically a complex function, and it is given by expectation of e to the power itx. So this gives you the characteristic function, and in integral terms it is defined as that is so this is how the characteristic function is found. One important property is, note that is less than equals to 1. And this is important because we see, since now when we are going to understand the modulus of e to the power itx fx, let us do that separately. Since due to Euler's formula, e to the power itx is written as cosine of tx plus I into sine of tx. Therefore, mod of e to the power itx is simply mod of cos of tx plus I into sine of tx. This in turn evaluates to root over of cos squared tx plus sine squared tx, which is just 1, right? And since this happened, we can say that now we can remove the modulus from the probability distribution function because it is always non-negative. So it does not make any sense to use the absolute value function here, but for the e to the power itx part, since it's a complex function, its modulus is 1, and that gives you this integral, which is basically the total probability, right, which is always 1. So this establishes that therefore the modulus of the absolute value of the characteristic function is always less than equals to 1, or the absolute value function always lies between -1 to +1, the absolute value, right? Okay, so this is the characteristic function, and we can do that for our exponential distribution. Because we have phi x of t equals to integration over the real line e to the power itx fxx dx, where fx of x dx it basically is equals to lambda into e to the power minus lambda x dx, right? Now therefore phi xt, since the region of integration is just 0 to infinity, we can write this as e to the power itx into lambda e to the power minus lambda x dx, and this would give us lambda times 0 to infinity e to the power, you can take minus x common again, and it will be lambda minus it dx. And using the same rules, we do not actually care right now that if I is a complex variable, just know that it will evaluate to lambda by lambda minus it, which is the CF, or the characteristic function for exponential distribution. So we have evaluated all possible properties of the exponential distribution, which we shall do for all other distributions that we are going to study from now on. So in this video we have ended our discussion about exponential distribution. From the next video we shall start talking about various other distributions like normal distribution, which is also called the Gaussian distribution, then there is the gamma distribution, the beta distribution, the Cauchy distribution, and so on. So I'll see you in the next video. Thank you for watching. So please download the Breatter Maths app, which is given in the description. It is a mathematical app where you can find all the necessary statistical calculators like chi-square calculator, one variable means, population means, t-value, and much more. You can also find calculus related calculators like integration, derivatives, There is a section where you can find what's coming up next. There is a section completely devoted on mathematical notes, where you can find notes on probability, statistics, calculus, and many more are there to come. In those notes, we have already explained all the examples, all the problems and theory, and we are just covering the video lessons and solutions of those here. You can check that out. Also, you can see the video solutions in a separate section where you can understand and give a feedback on what to expect next. You can ask for a problem, you can ask for a theory section as well. So please do check it out, and also do subscribe to Breatter Maths app and also its YouTube channel.